Bismillahirrahmanirrahim. In this lecture, we are going to study effect of field change on the synchronous motor and then synchronous condenser and the starting method of synchronous motor. Till now, we study the effect of load change, that when we change the load on the synchronous motor, then which parameter of synchronous motor will change. And now we are going to study that if we change the field current, then how synchronous motor will behave and which parameter of synchronous motor will change in this condition. So what effect does a change in field current have on a synchronous motor? So this is the figure shows a synchronous motor initially operating at lagging power factor. The phasor diagram, this is V phase, this one is EA, and this is IA, this is delta. So this is the phasor diagram of the synchronous motor when operating with the lagging power factor. So now we are going to increase the field current and then we will see that which parameter of the synchronous motor will change. So as we know, if we increase the field current, the EA will increase. We already studied that. So EA will increase, this EA will increase in such a way that this straight line representing the real power supplied by the motor, this will remain constant. So when we will increase IF, EA will increase in such a way that this portion will remain constant. So EA must increase, but it can only do so by sliding out along the line of constant power. This effect is shown in figure like this way. So that's how EA will increase. Like this. So this EA will increase along the constant line of action. So then corresponding J of XS IA will also change regarding this, and the magnitude of IA will also change. From this figure you can see that now the IA, when EA value is higher, magnitude is increasing, IA becoming leading. First IA is lagging, then less lagging, and then it will become leading. So this is the effect of IF on the synchronous motor. When we will increase the field current, that's how synchronous motor will behave. So notice that as the value of EA increases, the magnitude of the armature current IA first decreases and then increases again. From this figure you can see when value of EA constantly increases, then IA is the magnitude first increasing, then decreasing, and later it will also increase. IA value is also increasing. This is shown from this graph. So at low EA the armature current is lagging. Here IA is lagging, and the motor is an inductive load. It is acting like an inductor resistor combination and consuming reactive power. At low EA or at low IF, IA is lagging and motor is consuming reactive power and behaving as an inductor resistor combination. consuming reactive power, which is Q. So as the field current is increased, the armature current eventually lines up with V phase and the motor looks purely resistive. This is here IA2. When increase the magnitude of EA increase by increasing the field current, the magnitude of IA decreases, but now it becomes in line with the V phase. When IA is in line with V phase, therefore the power factor at this point is 1 and load is purely resistive and motor is not just supplying the real power and no reactive power either supplying or absorbing by the motor. So as the field current is increased further, so if we increasing the field current further, the armature current becomes leading and the motor becomes a capacitive load. From here IA3 and IA4 you can see that when magnitude of EA is increasing, the IA is becoming more and more leading and its magnitude is also increasing. So in this, at high value of EA or IF, IA is leading and motor is supplying reactive power to the system. Supplying reactive power Q to the system. So a plot of IA versus IF for a synchronous motor is shown like that. If this is IF and this is IA, so when IF value is small, at that time IA value is high. When we are increasing IF and EA, the magnitude of IA is decreasing and it is becoming less and less lagging, and when at this point, when IA have a minimum value, at this point the load is purely resistive and no reactive power is supplying to the load to the system, and when we are increasing IF further, the current becomes more and more leading and now it is supplying reactive power to the system. This is leading power factor, this is lagging power factor at specific P, for example P1. This is for leading power factor and this is for lagging power factor. So such a plot is called, this plot is called V curve for the obvious reason that it's shaped like the letter V. There are several V curves drawn corresponding to different real power levels as shown here. For different real power there is different V curve. For each curve the minimum armature current occurs at unity power factor, this one which I told you, at unity power factor, when only real power is being supplied to the motor. At any other point on the curve, some reactive power is either consuming by the motor or is either supplied by the motor. So therefore, by controlling the field current of the synchronous motor, the reactive power supplied to or consumed by the power system can be controlled. If we control this IFA, we can control this reactive power which motor is consuming or supplying. So on another terms, this equation can be this concept can be given as when the projection of the phasor EA onto V phase, like this is EA its projection on V phase, which is EA cos theta, is less than V phase, when this is less than V phase, then at this point current is lagging, IA is lagging. So at lagging current, motor consuming reactive power. Consuming reactive power Q. So when EA cos of theta is greater than V phase, when its projection is greater than V phase, so in this condition, when EA cos theta is less than V phase, since the field current is small in this situation, the motor is said to be under excited. At this condition, when IA is lagging and motor is consuming reactive power, the motor is called as under excited condition. So in the next case, like this, you can see that when EA projection on V phase is greater than V phase, then IA is leading. Then here IA is leading and motor is delivering or supplying reactive power to the system, and in this condition the motor is said to be overexcited condition. So this is overexcited condition. So it means when we run motor in overexcited condition, it means that its value of IF is high, and when value of IF is high, IA is in leading mode and motor is supplying reactive power to the system. This is overexcited condition. So now example 6.2. Example 6.2 states that the 208 volt 45 kVA 0.8 power factor leading delta connected 60 Hz synchronous motor of the previous example is supplying a 50 horsepower load with an initial power factor of 0.8 power factor lagging. The field current IF at this condition is 4 ampere. Sketch the initial phasor diagram of this motor and find the values of IA and EA. From the previous example, the electrical input with all the losses included is P in 13.69 kilowatt, and IA can be calculated as divided by 3V phase cos of theta, and from here IA is 25.8 angle minus 31.8 degree lagging. So EA, we already know the formula of EA. In the case of synchronous motor, it is V phase minus J of XS IA. XS value is also given in the previous example. By putting these values and putting current this value here and V phase this value, the result EA is 182 volt angle minus 17.5 degree. So the result is shown here, this one on which cursor is flowing. This is EA, its value is 182 volt, magnitude is 182, angle minus 17.5, and this is V phase, which is 208 angle 0. So now part B. Part B states that if the motor flux is increased by 25%, sketch the new phasor diagram of the motor. What are EA, IA and the power factor of the motor now? If flux is increased by 25%, it means internal generated voltage EA will increase 25%. So it is given as this: EA2 is equal to 1.25 into EA1, and it is equal to 227.5 volt. However, when EA will increase, the constant power will remain constant, which is the vertical distance from V phase to the EA straight line. So if this can be represented by EA sine of delta 1 will be equal to EA2 sine of delta 2. By putting here, the delta 2 value will become minus 13.9 degree. V phase minus J of xs IA2. From here, IA2 is IA2 is equal to V phase minus EA2 divided by J of xs. So the value of IA2 is 22.5 angle 13.2. Now current is leading and power factor is 0.974 leading. The resulting phasor diagram is now this one. This is EA2 and J of x IA, and now IA is this one, which is leading. So now the next topic we are going to study is synchronous capacitor or synchronous condenser. A synchronous motor purchased to drive a load can be operated overexcited to supply reactive power Q to the power system. As we know, in the overexcited condition, IA is leading. So IA is leading. So at that condition, when motor is running, it is delivering reactive power to the system and improving the power factor of the system. In fact, at some times in the past, a synchronous motor was purchased and run without a load simply for the power factor correction. So synchronous motor is used for the correction of the power factor. The phasor diagram of synchronous motor operating at overexcited condition at no load is shown in this figure. You can see that if this is V phase, so this is EA, because this is V phase, this is EA, because at no load power is approximately 0, so sine delta is 0 and delta is approaching to 0. When delta is approaching to 0, V phase and EA is very close to each other, and the resulting armature reaction, which is J of xs IA, can be given as like that, and IA is this one. So this is the overexcited condition at no load phasor diagram of the synchronous motor looks like, and when we examine it, we can see that this behavior is just similar to the capacitor, in which IA is leading V phase approximately 90 degree. Like these synchronous motors are used to improve the power factor of the system and connected to the system at no load. Since there is no power being drawn from the motor, the distance proportion to power EA sine delta and IA cos theta are 0. This distance is 0 between V phase because no power is delivering, and a very small power with just to overcome the losses are used. And Kirchhoff voltage law V phase is this: the quantity J of x Ia point to the left, and therefore the armature current Ia points straight up, and this is the straight up. If V phase and Ia are examined, the voltage current relationship between them looks like that of a capacitor, and this behavior is similar as the capacitor behavior. So an overexcited synchronous motor at no load looks just like a large capacitor to the power system. Some synchronous motors used to be sold specifically for power factor correction. These machines had shafts that did not even come through the frame of the motor. No load could be connected to them even if one wanted to do so. So such motors are known as synchronous condensers or synchronous capacitor. Synchronous capacitor. Condenser is the old name of capacitor. So the V curve for a synchronous capacitor is shown here. At this point, if this is IF and this is IA, at this point the power delivered by the synchronous motor is 0. So IA is approximately 0 at a unity power factor, and when IF further increase, so reactive power delivered to the system also increased linearly until the point of saturation reached. So that's how the synchronous motors are used as a capacitor. This figure shows the effect of increasing the field current on the motor phasor diagram. So this can see that when we increase the field current, EA increases. As EA increases, so corresponding IA increases, and corresponding IA increases. So it means more reactive power is supplied to the system. So we just increase field current and increasing the reactive power to the system. Now we are going to study that starting synchronous motor methods. Till now we studied that motor always assumed to be initially turning at synchronous speed. How this synchronous speed is achieved? How did the motor get to synchronous speed in the first place? This we will study now. This figure shows a 60 Hz synchronous motor at the moment power is supplied to its stator winding. If this is the rotor, and in the beginning at t is equal to 0, we assume that the Bs and Br are in phase with each other. So torque induced on the rotor is K into Br cross Bs, as delta between them is 0. So torque induced at that point is 0. Similarly, when Bs makes some 90° with Br as shown in the figure this, so at that point torque is induced on the rotor and it is in counterclockwise direction. It is in this direction. Similarly, now torque is induced on the rotor and rotor starts to rotate, but the frequency is very high. As motor literally starts to move, this stator magnetic field moves towards this point, and now it is making at angle 180° with Br. So torque induced again will become 0. So motor will not rotate. So now at next step at D, the stator magnetic field reached at this point. Here torque induced will become in clockwise direction, in this direction, and then again torque induced will become 0. As motor starts to rotate, then stator magnetic field will move faster and again torque induced will become 0. So in the one cycle of this frequency, the torque, two times torque becomes 0, and two times, one is in counterclockwise direction and one is clockwise direction. So motor will not rotate, and if there is some just a jerk occur and motor starts overheat and will burn. So there are some methods required to start the synchronous motor. Here it is explaining that during one electrical cycle the torque was first counterclockwise and then clockwise, and the average torque over the complete cycle was 0. What happens to the motor is that it vibrates heavily with each electrical cycle and finally overheats. So basic approaches can be used to safely start a synchronous motor. The first one is reduce the speed of the stator magnetic field. These are the starting method. The first one is the reduce the speed. Reduce the speed of stator magnetic field. So when we reduce the speed of the stator magnetic field, now motor rotor have enough time to rotate, and it will rotate with the stator magnetic field, and then we will increase the stator magnetic field speed by controlling the frequency. The second step is use an external prime mover to accelerate the synchronous motor. External prime mover. In this case, the prime mover is rotated by some external force, and now synchronous motor is behaving as a synchronous generator because external prime mover is driving the rotor, and some three-phase supply occur on the stator winding. Now the same steps are followed to parallel the generator to the system, and when it is synchronized with the system, then remove this prime mover, and now supplying the power supply from the stator side, and now motor starts rotating with the synchronous speed. This is the second method. And third method is use damper winding. So these are the three steps used for the starting of the synchronous motor. So now that's end from this lecture. Thank you.